Hello, and welcome to another session on data mining. Today, we are going to cover some preliminaries that will allow us to build linear models from scratch. And we begin our learning based on a very simple concept called gradients. So, if you're familiar with gradients and if you're familiar with gradient descent, you can perhaps skip this section, or otherwise, if you want to review this, join us. So, what we are going to cover today is first gradients and then gradient descent. So if you're familiar with the concept of functions, so a function is simply a mathematical way of expressing how one quantity changes as a consequence of one or more other quantities. So let's say if you've got a function, if you got, let's say if we want to model how an object accelerates when a force is applied on it, then we can describe that by this mathematical function. So we can say that this acceleration produced in an object is a function of two variables, the force that we apply on it and the mass of the object. So Newton gave us this function that the acceleration of an object is proportional to the force applied on it and inversely proportional to its mass. So we can represent that as this function. Okay, so it's again a function of two variables. If we keep the force fixed, then you can say that it's a function of a single variable, which is mass. And if you keep the mass fixed, then you can say that this is a function of a single variable, that is the force. But we can also analyze how a change in the force affects acceleration, or how a change in the mass affects acceleration. And that we can do using the concepts of derivatives. Before moving on to derivatives, let me cover a very simple concept called slope, and I know you will be familiar with it. So a slope of a line, let's say, allows us to measure what is the effect of along the direction on the y direction whenever we make a change along the x direction. So if I move along this axis, if I increase the value of x, what is the effect on the y direction? So if the slope of a line is positive, then that means if I increase the value of x, the value of y is going to increase as well. If the slope of the point of the line is negative, then that means if I increase the value of x, then the value of y is going to decrease. So that is what this slope allows us to measure. It's simply a ratio of the rise that in the y direction to the run along the x direction, and that's what we call slope. And then Newton and others came up with this idea of measuring slopes at different points on the function. So if your function is a simple line, then the slope is constant throughout, no matter where you measure it on the line. But if your function is nonlinear, like the one that you have on your screen, let me use a different color for this, please. And I'm going to switch to green. So if we have a different function, this red one over here, we can see that its slope is different. The effect of a change in x on y is different at different points on this function. And Newton and others formalized this concept in terms of what is called the derivative. So a derivative is a generalization of the concept of slope, in which we want to, when we take the limit along the run direction, that is, if we make a small change, an arbitrary small change along the x direction, what is the effect of that along the y direction? So that allows us to measure, and that is what is called the derivative. So in essentially what it means is that if I take a run along this x direction at this particular point, then I can calculate this delta y along the y and take a ratio of that. That is going to give me an approximation of the slope at this point. And if I make this delta x very small, then that is going to give me instantaneous slope at this particular value of x. And that is what we call a derivative. So derivative is nothing else, nothing more than the slope of a function. And as you can see, the slope of the function can change at different, and it can be different at different points on the function. So as you can see, in this region, let's say the slope is positive. That means if I increase the value of x, the value of y is expected to increase. The slope is even higher over here. That means if I make a change in x, the value of y increase more sharply. In this particular region, we can see that the value of x, as I increase it, then the value of y is going to decrease. So the slope of this function, or the derivative of this function at this particular region, in this region along the x, is negative. And if you notice and if you observe correctly, and you must have studied this in the past as well, that the slope of a given function at its maximum point is going to be zero. That means there is no, at that particular point, if you make a small change in x, the value of y is going to be constant. So that is why it's called the optimum point or the maximum point. So far we have covered what's the relationship between slopes and derivatives. So these are really good when you have single variable functions. But what if we have two variable functions or multivariable functions in general? Let's say the function that we took as an example of this acceleration function is a function of two variables, the force and the mass. How does the acceleration change for a given mass if I change the force? And vice versa. What is the effect of, how is the acceleration going to change if I make a change in the mass while keeping the force constant? Now, for that, we need to move on to another generalization of the concept of derivatives, and those are called gradients. So if you have a multivariable function, a function of more than a single variable, then what we can do is we can measure, let's say in this case, what is the change in acceleration with respect to the change in the force while we keep the mass constant. And this is what is called a partial derivative. We can calculate the partial derivative of this function with respect to the force. We can also calculate it with respect to the other variable, which is the mass. And I welcome you to calculate these on your own. What I'm going to do is to take a simpler function. So I'm going to take a function of two variables. I'm going to call the first variable x1, and then I'm going to call the second variable x2. And the function that I'm going to take is, it's the square of the first x1 squared, and then we have x2 squared. And if I take the derivative of this with respect to x1, the partial derivative of this function with respect to x1, then that means I'm interested in observing how the function value is going to change if I change x1 while keeping x2 constant. Okay, so if we calculate, go ahead and calculate that. You must have then done that already, but I'm just going to give you an intuitive understanding of this. So it's going to come out like this. And if I do that with respect to x2, then that is going to come out to x2. And then we can write the derivative, also the gradient of this function as, so this is nabla. So that's the typical symbol we use to indicate these gradients. And if we do that, then we can write this as a vector of these two quantities. So if you have two variables, we can its uh, write its gradient like this. So this is what is meant by gradients. If you want to read further on these, I welcome you to go to this Wikipedia page, which provides all the sufficient details that you need to understand. Here's a pictorial representation of the concept of gradients. This is a function, so there are two variables. One of them is x and the other one is y. At a given value of x and y, the function is going to have a value which is represented by this surface plot, which is in orange. So at a given value of x and y, let's say this particular value of x and y, you're going to have a certain value of the function. So imagine yourself at first on this xy plane, and then you can imagine looking up at what the function value is going to be. Now imagine yourself at this particular point on the function, and at that particular point, if you are interested in understanding whether the function is going to increase or decrease if I make a change in the x direction but not the y direction, then these partial derivatives allow you to do that. Similarly, if you're interested in observing what is the effect on the value of the function if I make a change along the y-axis, the y-axis is this axis in this case, then what is the effect while keeping x constant, then you can do that also using partial derivatives. And if you do both of these, you can calculate the partial derivative of this function with respect to x and with respect to y. Then you can get a vector at that particular point on this function that tells you the direction in which the function is going to change at that particular point along the xy plane. So I hope you are able to understand the concept of gradients. They're really simple. They're just a generalization of the concept of slope. So if you want to go back to the first principles, which is sufficient for our purposes in machine learning, Think of a single variable function. If you understand the concept of slope, how does the function value change with respect to a change in its independent variable with respect to change in x in this case? And if you can measure that, if it's increasing, then that means the function value. If the slope is positive, then that means the function is going to increase whenever you make a change in x or increase the value of x. Okay, so I hope you're able to understand this. Please go ahead and do read more on that in the Wikipedia page. The next thing we are interested in is how do you find the minima and maxima of a function? And you must have covered it in high school algebra or calculus in your high school. Okay, so if you're given a function, whatever that function may be, f of x, let's say if you've got a function of a variable called w, and let's say this is the function that whose function form is given to you, and you're interested in what are the maxima and minima values of these functions, then what you can do is take the derivative of this function and you can substitute that derivative is equal to 0. Remember, places of no change are either the optima points or they're the saddle points of that particular function. And then you can use this simple fact to compute what is the optimal value, what is the optima value of this particular function, which comes out to be 0.5 in this case. However, if your function does not have a well-defined derivative, uh, then it may be very difficult. Let's say if you have a function like this one, then computing what is the optimal value of w for this is going to be tricky. Okay, and we are going to discuss a method next called the gradient descent that allows you to find the optimal points of functions when you are not able to write a closed form formula for the optimal value of w. And to do that, I welcome you to imagine yourself on the top of a very smooth hill. So a hill like this one. So let's say if you're standing over here and all of us are one dimensional in this example. So there's only a single dimension and that is x along the x-axis, and then we have the height of the hill that we are going to call f of x. And let's say you're at the top of this hill and you want to get to the lowest value of this function or of this landscape. So what you can do is you can calculate, let's say if you are over here, you can calculate the slope of this function, which is going to be 0 at the maximum point, and that doesn't really give you any direction to move in. But if you take a small step to the right, in this case, then we know that the slope of this function is negative. So it has negative slope at this particular point. So the slope at this point is negative because the function is decreasing, right? So that means if I increase the value of x, then that would take me further down along the direction, along the height direction, along the y-axis. Remember, the slope is the direction in which the function increases. So in this case, since the slope is negative, that means if I increase the value of x of my current x direction, then I'm going to decrease my height. Okay, so that is what is called the gradient descent algorithm. So what we do essentially is at a given point, we calculate the derivative of that function. And if that derivative, let's say, comes out positive, then we decrease the value of x by a small step size. And if in this case, if the derivative of that function comes out to be negative, which is in this case, then if we increase the value of x, then the height is going to decrease. So based on that simple observation, what we can do in this case is take a step in the direction that increases x. So we're going to, let's say, increase x by a certain amount. Let's say if you're over here and your original value of x is, I'm going to denote that by x0, and then you can have a higher value of x, which I'm going to call x1. And if you take a step from x0 to x1, then what's going to happen is your function value is going to decrease. So this is the idea behind what is called the gradient descent algorithm. So this is a formalization of the same algorithm, and I'm going to go through the steps again. So let's say if you got a function represented by this blue line, that we are going to call L of W or F of W. This should be an F. Okay, so please don't mind that. Similarly, this should be an F. So if we have a function F, then what we of a single variable, let's say in this case W, and let's say we are currently at this particular position along the x-axis. So we are at W naught. We know that the slope of this function at this particular point is positive. So if we take a step along the direction of the slope, we are going to increase the value of the function. Let's say if you are interested in going to the minimum value, just like in our peak example, we wanted to get to the value floor, then what we need to do is to take a step opposite to the direction of the slope. So the slope in this case is positive. What we want to do is to take a step or along this axis, along the w axis, in the direction opposite to the slope, which is going to decrease the value of w1 in this case. So we are going to move to another value called w1. And at that point, we can see that the value of the function has decreased from fw0 to fw1. So if we keep on following this, if we come up to this new step, then what we can do is we can calculate the derivative again, which is again positive. And if if we decrease the value of this w, then that means the value of f is also going to decrease. So if we take another step, let's say if you move to here, then we can say that the value of the function is going to decrease. And if we keep on following those steps, eventually we are going to reach this value floor. If we start on the other side, on the other hand, if we let's say start on this point, if we take this as the starting point, we know that the slope of this function at this particular point is negative. So the slope is negative at this particular point. Then what that means is that if I increase the value of w, the function value is going to decrease. Okay? Coming back from the first description of slope that we talked about in the previous slides. So what that means, if I increase the value of w naught to another value w1 by taking a step along this direction, along this particular direction, which is again the opposite direction of the slope. So the slope is negative. So the slope is along this direction, but we're going to take a step along this positive axis. Then the function value is going to decrease. Okay, so we're going to go from fw0 to fw1. And if we keep on following these steps, then we are going to end up with this particular function. So this simple algorithm is called gradient descent. What it essentially says is that if we have a function f of w, then at a particular value of w, let's say at a value of w called wk, what you can do is take a derivative of this function with respect to w, and you change the value of w in the direction opposite to this gradient. So to take a step in the opposite, we multiply this gradient by this minus sign, and then we multiply it with a step size parameter, which we are going to call alpha, and we are going to add this to w. So if we have wk over here, this is wk, then we are going to end up at the next step. So if we keep on following this rule, then what's going to happen eventually is that we are going to end up at the minimum position of this function. So this is the concept of gradient descent. I have a piece of code that we are going to go through next that will allow us to understand this better. To summarize, we have covered the concept of slopes. So a slope of a function is, if it's positive, then that means if I increase x, the function is going to increase. And we have used this simple concept to identify the minimum position or the minima of a given function by an algorithm called gradient descent. And the way that algorithm works is the following. At a given point along the independent variable x direction, calculate the value of the function and calculate the derivative of that function at that particular position. If the slope comes out positive at that particular position, then that means to decrease the value of the function, I need to take a step in the direction opposite of the slope. So I need to decrease x, and that is going to lead to a decrease in the value of the function. If at that particular point along the x-axis, the value of the function, whatever the value of the function is, If the slope of the function is negative, then what that means is that if I increase the value of x, then I'm going to decrease the value of the function. And if I keep on doing that, if I keep on changing the value based on this rule, that is, move in the direction opposite to the slope, I'm going to reach the global minima, going to reach the local minima of the given function.